last lecture. And so today I'm supposed to give you guys an overview of advisable reinforcement learning research. And I understand that at this point, you guys may be tired, and this is at the end of a semester. So when I made the slides, I intentionally remove those technical parts and just keep those high-level ideas. And I hope you guys can relax and enjoy the talk. And the goal of this talk is mainly to help you guys to get a sense of what advisable reinforcement learning is and what's the ongoing research and what are the open challenges. So my plan was to cut the talk into two parts, but I found that there's already lots of things to talk about for the human in the loop reinforcement learning part. So today I will just focus on the first part, and I was supposed to talk about the RL plus some external knowledge, combining reinforcement learning and planning, like what we did in the ICML paper that Dr. Rao has been talking about it all the times, but I don't think we have enough time for that today. So I will just talk about human in the loop RL. Yeah. So I think most of you guys haven't heard about human in the loop RL that much before. So instead of in a normal presentation, I will start with explaining what is human in the loop RL first, instead of explaining the motivation. So the overall framework of human in the loop RL is we have a human trainer stand in the loop of the RL agent's training process. It's monitoring the learning process of RL, and when the humans find it necessary to give advice or give some feedback, the humans can just do it at will. And once the agents receive the feedback from the human, the agents can just adjust its policy according to the advice or feedback. So there can be many concrete forms of human feedbacks, and there can be many different interpretations of human guidance or human feedbacks. So I will list two representative method of human in the loop feedback. So one is to interpret human feedback as evaluation feedbacks on a certain state action pair. So here a critic is essentially a good or bad binary critics over the actions taken by the agent. So let's see here if the agent is taking a jump here, and the humans can maybe happy with that action, the humans will just give a good feedback. And what those representative works do is we train a neural network to approximate the human feedback, the human evaluation, and then we want the agents to to maximize such rewards coming from the human feedback, and such that the agents can take those learn a policy that satisfy the human and also maximize its performance. And another kind of interpretation of human feedbacks can be a preference over pairs of trajectories. And here let's look at a video showing how this system works. So at the beginning, the agents will just here, there's no human standing in the loop. So it's just the agents randomly taking actions in the environments. Because this is in a virtual simulated environment, there's no actual physical damage to the world. So it's okay to just taking random actions, or they can add some incentive to encourage the agents to more explore the world. So after this random action taking process, the agents will collect a few trajectories, and then the agents can query the humans for their preference over different trajectories. Let's see here that the human teachers will say, okay, I like the right one better. And then the agents, after receiving these preference labels, the agents will just update its reward function. It has a reward function that it will maintain a reward function that approximate the human preference. So with more feedbacks from the humans, the reward function will capture the latent preference of the humans better. And then the agents will just update policy according to the updated reward function. And the agents can with the updated policy, it can collect more trajectories or experience from the environment and then query the humans. So the process repeats until the agents learns a good enough policy. Let's look at the video. So now the agent has collected 250 feedbacks from the humans, and it still fails to stand up. It gets a little bit better, right? Right now it can stand up. Now it starts running a little bit. So after 500 feedbacks, it looks like the agent is able to run a barely usable policy, but it's still not that stable, the motion. So finally, it learns a kind of good enough policy. So you guys know how this kind of framework works now. Another thing I want to highlight is this kind of learning from human preference method, not just works for a character or robot control task. It can also be used in natural language dialogue system and a summarization task. So yesterday, about two days ago, the OpenAI just released their latest GPT-3-based dialogue system, and you can go to their webpage. I don't know if you guys noticed this. So actually, they use human learning from human preference, that kind of method that we just talked about. They use this kind of techniques in training, in fine-tuning their chatbot. So I can briefly talk about it here. So in their first step, they just do imitation learning. So they have lots of prompts, and they have labelers to provide a human demonstration, human answering to those question given to the GPT model, and the GPT model is fine-tuned on those human demonstration. And the second step is where the learning from human preference comes in. And so right now the chatbot models might give some imperfect answers to some questions. So OpenAI recruits a group of labelers to rank the outputs of the chatbot, and with those rankings over candidate answers, they will learn a reward function according to those rankings. And then the last step, after we learn the reward functions, they use popular reinforcement learning algorithms to further train the chatbots. and to fine tune its outputs. That's how they get the latest GPT model. You can all go to like their web page and play around it. I think they are still public right now. So I think now we all have some sense of how like the latest learning from human preference or like learning from human feedback works. So now we are going to answer why do we need those kind of techniques? Like so what are the alternative ways to like construct like rewards or like any kinds of like a supervision signal to the IO agents? So there are several reasons why we need those techniques. One is like reinforcement learning is usually very slow, like especially when it starts from scratch. It needs like 1,000 or like millions of like environment samples to learn a usable policy. So if the humans can provide like advice or like a denser supervision signal, we can speed up the entire process. And also like different users, especially different end users, may have different preference over the behaviors of an AI model. So if we allow the agents to adjust its behavior according to the user's feedback, we are able to align its behavior to the user's specific preference. So more importantly, like sometimes a closed form symbolic reward function is hard to give. So especially when the task involves taxi knowledge and both taxi knowledge and explicit knowledge. And if the user is not an expert, such rewards is very hard to design. So I can give you an example here. Like for this is like a very famous task in those like a popular benchmark. I get it from the DeepMind control loops, and there's also a version available in the OpenAI gem. So the default symbolic reward function is just like the agent is supposed to like walk or run at above certain like a speed. So when the agents optimize the rewards, it usually end up learning a policy that like a walk or run in a very unnatural way. You can see here it's not, human never works in this way. But the problem is like how can we, like if the user wants the agents to move in a human like way, like move naturally, how can we define like the way of working naturally? So there's no way, this is a fully tested knowledge test. So there's no way for us to like symbolically like define such reward or such constraints. So the only way is to like we compare, like ask humans to provide evaluative feedbacks or ask humans to like compare two different ways of like working and yeah. So in that way, we can like we can indicate our preference over the motion style. And this example is what we get from the previous like the learning from human preference. It works. Yeah, I get it from there. So also like another example is like let's record the GPT-3 model. Like so it's very hard to like define what is a good answer, right? It's like sometimes it's subjective and sometimes it's like it's all about natural language. So it's hard to like define why like this answer is good. So the easier way is to just give like an ordering among like candidate answers. So in that way, we can construct a reward function or evaluation function. So we can see that like those kind of techniques are very like flexible, very expressive, and very powerful, but they still have several like many like issue limitations. One is like they need like so many data. So let's say in the previous example, the preference-based IL takes around like 1,000 feedbacks from the humans. Let's say if giving one labels takes 20 seconds, and so to give those like 750 pieces of feedbacks, the human labelers will need like around 4 hours. that's not like a feasible number, like for any real world applications. And to train the GPT, the OpenAI has to partner with two like data labeling companies. Maybe you have heard about them, like Upwork and Scale AI. And it's so expensive. So even the, yeah.
So you mentioned every single trajectory they have to provide feedback on to train it?
Not necessarily. Like, oh, you mean in the learning from preference?
Yeah.
Yeah. Every time the agents present to a pair of like trajectory, the human has to give preference. But that preference can be like they are equally preferred. They're not necessarily like a one is better than the other. Yeah. So this is so expensive, even the OpenAI team themselves don't want to do it, yeah, internally. So they have to like outsourcing the labeling. So it's not affordable for a team like OpenAI. So it's not affordable for us, for our like ordinary people. Yeah. So one reason why like a question.
So the previous task which you showed, does the number of feedbacks or number of epochs it requires to learn the policy remain same across many runs?
Sorry, can you repeat?
So if you run it again like from scratch, will it always converge after the same time point or after the same number of?
Not necessary. That there are some like around that amount, that number of feedback.
Okay, so like I wanted to ask like what's like the variance in that, like how much does it fluctuate? Is it like,
I mean, it depends on the task. Like this, the working task, like usually it will convert with around like 1,000 feedback.
Okay.
Yeah.
Okay.
So if you check out the paper, they will show the variance. They will show the learning curve, like the performance of the agents, like against the number of feedback they receive from the humans, and you can see they will show the shading area represent the variance. Yeah. So one reason why such like a system is so ineffective, so inefficient is like to me is binary labels are not very informative about the user's preference. Like let's see an example here. Like there is a taxi agent, and the agent is supposed to pick up a target passenger. So when the taxi is moving right towards the right side, the humans give a good feedback, like because the taxi is like is getting closer to the target passenger. But this good feedback doesn't indicates what is the true target. So the targets can be like the passenger in red, the passenger in yellow, or other passengers. So it's not super like informative, the binary feedbacks. And our argument is like in a large number of cases, humans are able to explain why certain actions are good or bad. So why don't we allow them to explain it? So this motivates the idea of expand. So so in that world, we are essentially widening the communication pipeline between the humans and the agents by allowing them to like in addition to the binary feedback, we allow them to like give some kinds of explanation. And here there we say the explanation are visual explanation, which meaning like which means the humans is giving some kinds of like highlighting some task relevant regions in the state they evaluate. So let's see here in the taxi examples, the humans when the agent is moving right, and the humans might highlight both the test agents and the target passengers. And that way, this is a very like very informative supervision signals for the agents. So, and with that, we hope that the agents to like can figure out the human preference much faster and takes much less like human feedback. Yeah. So the problem is like now we have the human's feedback along with visual explanation, which are the human's attention or like relevant regions, relevant pixels in the image state. How do we? The problem is how do we incorporate those like attention or like those saliency informations into the training process of the RL agents. Now, suppose we are using a deep RL. We have a CNN here. So yeah, and here we use kind of like a data augmentation methods to like inject those knowledge. So here the example is like as we say, like as I just said, the human is highlighting relevant regions against task irrelevant regions. So it means the irrelevant regions in the image are not like affecting the ground truth actions. So we can make some like a small change to those relevant agents, irrelevant region, and we expect the agents to be like invariance towards those perturbation over irrelevant regions. So we do data augmentation, perturbation. We use like Gaussian blurring to blur out those like irrelevant regions, and we apply a regularization over the CNN, the policy networks, and force it to give the identical estimate over the Q values. So our like empirical results show that like this kind of trick, I would say it's just a trick, like result in like a 35% of reduction in both environment sample and human feedback sample required. So it looks like a big number, like 65% reduction, but I would say a 35% reduction is still not enough. We still need a super large number of like human feedbacks. So I will say like no end users will be patient enough to give that number of human feedbacks. So the question is, can we further improve the systems? So my thinking is like expands takes like task relevant regions or task relevant features as like auxiliary informations to help the agents, but in fact those like information are still like low level. It's not like so it's not like how the humans like communicate their preference, their intents in terms of concepts. So the ultimate way to support like human teaching or human agent communication should be at the level of concept whenever concept is available or the human preference is disquiettable with those concepts. So, but to proceed to come up with a system that supports concept level like communication, we have to figure out to understand why can we assume the user's preference is describable in terms of concepts, and we have to decide whether it was the overhead to take extra steps to model the concept. So, and here to understand when we could use concepts, here I will give an example here. So the green box highlights the exact symbolic goal specification is fully in symbolic concepts, and the left side is the learning from human preference we just discussed. So let's see the assumptions behind those different approaches for learning from human preference, which is essentially like a pairwise trajectory comparisons. It assumes the humans can only give those binary preference label and no other it's fully tested, and no concepts or any kind of symbols can describe the user's preference. It's true in some tasks like the agent, the running a task I just give. So it's true there, but it's not. The assumption doesn't always hold in all the tasks. So, and on the other hand, in exact symbolic goal specification, this approach assumes the humans can like give a full specification of the objective using symbols. So it's very straightforward and intuitive to use because it's at the level of concepts of symbols, but it's also limited to like a explicit knowledge task. So, so our standpoint here is like, I think for a large body of tasks, not all the tasks, for a large body of real-world tasks, there essentially involves a mixture of like text knowledge and explicit knowledge. And even when the end users cannot construct like symbolic rewards like completely, and they still able to describe like how they want the agents to change its behavior to better like satisfy the user's requirements. So the example here is like for working agents, the users might want it to like move more softly. So the softly here is the concept like corresponding to the user's preference. And the users might also want the agents to like take a bigger step. And the step here is the concept. So here we assume the agents have some kinds of text knowledge itself. It's like it already knows how to work, but like the users might prefer like have a different preference over some kinds of concept, behavior concept or behavior attributes. So as a summary, like we have like for pairwise trajectory comparisons, like it's a general enough settings to work with for any kind of setting, for any kinds of like a task, but sometimes it's unnecessary, like it's unnecessarily expensive, and it spends like take a step towards like a multimodal communication or like towards richer supervision from the humans, but it's still not at the concept level. It's still at the level of like a pixel, and so it doesn't like fundamentally like change like avoid the limitations of this kind of approach. And on the other hand, like exact symbolic goal specification, it's preferred or is only applicable when the objective is not very complex and can be like described in terms of concepts. So here is what we are going to discuss, the relative behavior attributes. So here we assume the task involves both tacit knowledge and explicit knowledge. And the agent builder is responsible to give the tacit knowledge part. It's like it first construct attribute parameterized rewards that encodes knowledge about like how to work in a human-like way. And then it will pass the like attribute parameterized reward functions to the end user and allow the end users to customize the explicit part, which like which is at the level of concepts like step size, like movement softness. Here I give two examples, like the users might want to adjust the sharpness of steering behavior of like autonomous driving agents, or adjust the softness of like a working agent. For a full example, let's take a look. You can like ignore those like a detail number. We will revisit them later. So here the figure, the numbers under each like a state shows the ground truth step and ground truth softness of the agent's movement. We can see like the agents can always change its behavior like up in the direction like specified, highlight by the end user. Like every time like let's say here the users wants the agents to reduce its step size and increase its softness. You can see that the agent is able to like adjust its behavior in that meaningful access of variation. And this is like very satisfactory for like for real world application. Like end users are not always patient enough to like give like preference to give ranking over different like even random behaviors. But here we can, the end users might feel like he or she has like full control over the agent's behavior. Like the agents always follow its the human's instruction. This brings very good user experience. And also it's very like efficient. Let's see, like here, it only takes the humans for takes 4 attribute level feedbacks from the humans to get to the desired behavior. So it's extremely efficient. So let's see how I implement, realize the functionality of the relative attribute, behavior attributes. So in the papers, we have come up with 2 different approaches to realize the functionality. But here, let's look at the first one. So the first approach is very straightforward. Firstly, we can construct a global ranking over possible behaviors. It's we suppose we are given a diverse set of offline behavior data sets, like the humans, like for the Waymo driving data set, there contains humans that taking different sharpness when making lane change, or there's a human motion data sets that work in different styles, and the humans take different step size, and we can use those motion data sets for a virtual character control task. And so the first step is to establish the global rankings over all candidate behavior. Let's say for attributes, movement, softness, we are essentially learning a functions that give us scores to any behavior that corresponds to, and the values of the attribute score corresponds to the strengths in the behaviors of the agent. It's there's a ranking over all possible step size, and the model is learned to give approximate that ranking. Basically, give an abstract scores to the attribute strength, and with that abstract attribute strength score, we can then learn a reward functions that can generate any behaviors that specified by the target strength. For example, here we say we want the agents to have a softness score of -10, and we want the agents to take a step size of 15, and the reward function is supposed to generate that behavior specified by the input target. Is it clear? I think it's should be very straightforward, right? Yeah. So in the actual interaction process, the only thing the agent needs to do is to adjust the inputs to the final reward function. Let's see here, let's look at this part. So when the human say the human wants a bigger step size and a smaller softness, the agent just need to increase the input target step size score and decrease the softness score, and that reward functions will results in a behavior that's specified by the input target. So there are some limitations of this kind of a global way. So one is we can see here, every time to produce agent behavior, we have to specify all the target score of all relevant attributes. Here is okay because we only have 2 attributes. But what they found, let's say we have household robots that needs to maintain 100 attributes at the same time. Do we want the user to set those 100 attribute score every time? And that's definitely not good. So, and also there has some scalability issues. And so in this second approach, what we want to avoid is we want to avoid the maintaining of those the target attribute scores. So instead, we can skip the step of establishing global rankings and directly learn the behavior editing rewards. That is let's say we have current behavior of the agents. Let's say the agent is working at a step size of 0.5, and by inputting the current behavior into the reward function and the relevant attributes and the direction that the humans want the agents to change the behavior, we want the reward function to give higher rewards to a behavior of working with a step size of 0.6, which increase the step size. But at the same time, we want the rewards to make minimum change to other behavior features related to other attributes. The good thing here is every time the function the humans only indicates one attributes of interest, and we only need to pass that attributes of interest into the function. So we no longer need to give a full specification of all attributes. So it's much more scalable. And let's look at an example. So let's see here. The human says the agents should take a bigger step size, and then with current behavior, let's say the behavior at Q3, we pass it into the reward functions, and also give the attribute of interest, which is the step size and the direction, which is increasing. So and then the reward function will give us updated behavior, which has a bigger step size. And then we also increase the softness, and we do this in the same way. And finally, by optimizing these updated reward functions, we are able to get our updated behavior, which is changing in the direction specified by the human. So basically, our second approach is doing almost the same thing as the first approach, but it's more scalable in terms of the numbers of attributes it can encode. Yeah, that's basically all I wanna discuss today. And yeah, clearly there are still some limitations in our approach. And if you are interested in them, feel free to drop me emails or
Can I ask you a question about the Gaussian blur filter in slide 13?
Slide 13.
Yeah, I was interested to see
This one?
or actually maybe it was a slide or two for it. But specifically, is there a reason you preferred Gaussian blur filtering for normal distributions instead of something like Gibbs sampling?
Okay, you mean here?
Yeah, that's one. Yeah.
Yeah. So the problem is when we're doing perturbations, we don't want to introduce new elements to the state. So there's some popular augmentation methods like cuts, the random cuts. We have we randomly put a black block to hide something in the image space, but that a black block might have some specific meanings in some task. You see what I'm saying? In some game, there those block can have some specific, maybe it's some kinds of game objects. Right. So we want to avoid those kind of those kind of augmentation that change the state context.
That makes sense.
So the Gaussian blur is it's the most safer. It's a safer way to do perturbations.
Okay.
It's not the only way. You can see many other papers that applying different kinds of perturbation, and it's still an open research topic. Yeah. Any other questions? Okay, and do we have to take a break or? No. Okay. And I will pass on to Siddhant to talk about his research.
Hello everyone. Just two logistical things before I start. Make sure that everybody has signed the attendance sheet before they leave, and whosoever has got the cheat sheet can just leave it at one of the desks later towards the end of the class. Okay, most of you would have heard about the game Wordle, which became really popular starting this January in the pandemic. And so this was, this interestingly was a type 1 project when I took this course with Professor Dimitri Bersikas in spring 2022 this year, along with my co-author, Amrita Bhattacharjee, who's a PhD student from Professor Guan Liu's lab. Just get started. So just a brief recap on POMDPs. I've used some slides from Dr. Rao's slide deck, just 2 lectures back. So POMDP comes in this vast set of formalisms for planning problems, where we usually see partially observable state space. And a formal definition of POMDP, I'll just quickly go through this, but feel free to ask questions anytime. We have a state space, the action space, the transition, rewards, which are same as an regular MDP. Then we have an observation, which essentially is because of the partial observability that we are getting for the agent. And then the observation function, which is essentially a mapping from the state and action pairs to the observations. And the belief state is essentially what we call as what the agent's belief is over, which you can think of as a probability distribution over the different states that the agent might be in. And the task is to be able to define that belief state as you progress in the environment. The task is simple to basically maximize the goal or the reward that the agent is getting by interacting with the environment. And this, given that the partial observability constraints for the agent. When the agent has to act, it basically starts with the belief state, takes an action, sees what the updated belief state is, based on the observations that it gets from the environment. And one of the ways, or one of the nicer ways of updating this belief state is using the Bayesian update rule. So this was the example that I think Professor Rao mentioned in the class also earlier, where you started with an equal probability over the 9 different states in the first grid world. As you took an action, the probabilities started updating, and over the time, when your belief had a dominant probability over the top right corner cell for that grid. So yeah, that's just a small recap on the POMDPs. For those of you who don't know about the game, this was just an online game published by New York Times. And there's a new word that is available. We'll call it the mystery word, which is selected from a mystery list, as I can call it, just a list of 5-letter words. And then there are these guess words that I can use to see, to basically get the observations from the game. What the environment is giving me is the observations here. So if the alphabet, for example, in the first simulation, if I'm playing the word turn in the second step, T essentially is coded yellow, which basically means that the alphabet is in the word, but it's not at the correct position. And for the green alphabets, they are in the correct position too, and the gray ones are just not in the mystery word. So that's pretty straightforward for the rules of the game. There are two modes of the game. There's an easy mode and the hard mode. The easy mode does not have any specific constraints. But for the hard mode of the game, for example, if I played the word cars as the first step and got a green observation E, I have to make a word on the next step which has an E in the end. And if it's a yellow observation, I have to play another word which has, so I cannot change. For example, I wouldn't have played the word stern in the hard mode if I got I as the yellow observation, because I had to make an I in the second guess as well. So that's the distinction between the easy mode and the hard mode. And the hard mode just adds more constraints to the game. So how do we see Wordle as a POMDP? It's a straightforward idea here too. The states here are essentially what I'm tracking the mystery words. So maybe after I receive an observation, say when I played the word stern, my mystery word set should contain the words which have the alphabets T, E, R, and N. And they might be at different positions. Maybe ER at the same position if it's an hard mode game. The actions here are essentially the guess words that I'll be playing. Transitions in this setting would be basically the probability of going from one mystery word set to the another mystery word set when I played a game, when I played a guess word. The rewards, in fact, here can be taken as cost. So think of it as negative rewards simply. And the cost is here that I need to finish the game within 6 steps. So that's what I'm trying to minimize here essentially, instead of saying maximizing the reward. The observations are the colored observations which the environment is providing. And since the environment is the simulator here, in a way, it is playing the role of the observation function. Because there is a state, I play an action, whatever the observation is, the environment gives me that. So that's how you can see the direct application of simple POMDP, where you have deterministic belief states and deterministic actions, which would just lead you to a belief state where you know that this one word is the final mystery word, and then that's when the game ends. So interestingly, a lot of people tried a lot of mathematical and computer science methods to solve the game. It was good to see that a lot of literature already started publishing on this work, on this game, at least using the game as just a test bed. But it's interesting to see the application of certain ideas that we come across in courses, and that was the same case for us as well, and how we can apply it to the games, to real life games like this. So dynamic programming, in short, you solve the game by solving small substructures of the problem. For an optimal solution for this, you can imagine this as a decision tree that given an observation, what are the possible mystery words that you can actually lead on to with that particular decision tree. Solving this with optimally using a dynamic programming approach is, and especially if you use back propagation in dynamic programming, it's completely impractical given the enormous state space size. There are 2 works currently that actually found an optimal solution by running the program using recursion over multiple days, in fact. So that's how computationally inefficient, I would say, finding an optimal solution is, but it's a good benchmark to have at least. One interesting concept that we try to put forward here is the use of rollouts. So think of it in this way, that when we were talking about the optimal solution, given an observation, I would like to take an action as an agent. Now the action should be such that whichever the state action pair should give me the optimal value function for that state action pair. Now think of it as, we can call it as V star, which is the optimal value function. Now, since I said that computing this V star is inefficient computationally, what could be the ways that I can calculate an approximate V such that it is not too far away from V star and I can still solve the game in a much more efficient manner. So rollout essentially is a method. It's easy to understand it in this way, that it's a method to approximate this value function. So what is happening is, imagine that by capital M, I'm calling the state, which is the mystery word set. So in the beginning, you have about 2,315 words. As soon as you played a guess word, maybe your search space reduces. So you might have, say, 200 words at the next step, and so on and so forth, till you reach just one mystery word, which would be your answer. So imagine that you are at the current state, MK, we'll call it. And now you need to choose an action UK that would lead you to the next mystery word. So before choosing that, what we do is perform a rollout. Now, I would have multiple actions that I can take. Maybe there are like 100 guess words that I can use to make the next guess. For all those 100 guess words, there might be about I'm just making up the numbers, 50 mystery words that could be possible at this stage. So for all these words, I can play the rollout using a base algorithm, which I'm calling a heuristic, and I'll come to that in a minute. I can see if I keep playing, if I start with that action word at stage K, and I reach the end where I can find a single mystery word, how many number of steps did it take to solve all the 50 mystery words using every starting possibility? That's essentially what we are calling the rollout as. You don't have to search in the entirety of the space, like what the optimal solution would have been, like at least brute force method would have been to search like, okay, if I'm at this stage, I would search among all possibilities, and among all possibilities, even at the next stage, I'll look at all possibilities. I'm not doing that. I'm cutting off a lot of search branches in this way by just using the base heuristic algorithm to reach the end where I'm just remaining with one particular guess word. So one mystery word, basically when I have a complete belief about the answer. So what is this heuristic used? In case you got a chance to watch the 3 Blue 1 Brown video, which was popular for, one of the first persons, Grant, he was one of the first persons to come up with the heuristic to solve the game. I shouldn't say come up with the heuristic, but the application of information gain or information entropy calculation for this game. So what information gain essentially is doing is, it's cutting down the search space, as I said. The higher the entropy for a word means how much information am I getting by playing a guess word such that my information space is reduced. So I would try to cut down my search space as much as possible in the beginning so that I can be left with only one mystery word in the end. So that's what the heuristic is doing for us. You can think of, like, in case I'm looking at a shortest traveling salesman problem, the heuristic can be a distance function. It's the same thing. Actually, the rollout method has been discussed with the traveling salesman problem as the key example. So you can make connections with that too. So that's the base heuristic, and we can just use this heuristic, and there are many approaches also which we can try. And we did in the paper also to show that the work that the method rollout method can actually incorporate any suitable heuristic and improve upon its performance. So how are we solving the game? So we start with the base heuristic scores for all possible actions that you had the 100 guess words that you could use. I basically say calculate the entropy for each of these 100 guess words and rank them accordingly, that based on how much search space they are reducing at a particular stage of the game. Once I have these rankings, I can select a subset of these. Performing the rollout over all the guess words would just increase the computation time, but it's an empirical observation that even like top 10 ranked words were sufficient enough to give us really good results in that way. So from the diagram, if you can observe that I'm just using this UK1, UK2, UK3, maybe just the top 3 ranked guess words that I can use and perform the rollout on. The next stage is for each of these guess words, I solve all the possible mystery words that are possible in the current game and calculate the scores for these. For example, if one of the words is reaching 10 mystery words in about an average of 3.5 guesses, so that would be the approximate Q factor or approximate Q value for this. This is the approximate value that I'm calculating instead of the optimal solution. So that's where the key difference comes from when I'm saying that I'm approximating the Q factors for these. And I just take a mean over the number of words. So the average number of guesses that a word would take at that time. And then the word that yields me the minimum Q factor, which basically minimizes the cost or maximizes the reward in that sense, I would just select that and take the next step. So that's the rollout algorithm. Now, the advantage of using this rollout method from the heuristic point of view is, just to mention the results, the optimal score was using the word starting with Saleh was 3.50, and even with rollout, we got a score of 3.52, which is less than 1% of a difference from the optimal score. The key advantage, the game was solved within seconds instead of multiple days. Which is, and another interesting observation here is, if you look at, so all the plots that are marked with stars or crosses are actually the plots with base heuristics. And I'm just applying the base heuristics without the rollout, and with rollout, the plot lines with the circles. So essentially, if you see the base heuristic, if I use the maximum information gain, which is shown in blue, the rollout essentially brought down the average number of guesses for all the starting words that we tested on. And these are all the starting words that different works have proposed, which according to their strategies were the best openings. So the point is to show that it's pretty independent of which starting word you are choosing. Whatever the base heuristic gives you, the rollout method essentially improves upon. That's the key thing. And even for one another heuristic that we see in red, that was doing pretty much better than the information gain heuristic. But still the performance by rollout was almost equivalent to the other rollout performance. Basically, you can see that the difference between the performances of these heuristics is washed away when you are using this method. I think those of you who took class 471 with Professor Rao, the A-star search was a very important topic back then. And I'll come in a minute why this is a good connection to make here, which is one of the primary takeaways, at least for me on a personal level too. So in A-star, imagine that you had a node graph where you were trying to find a path with optimal cost, minimum optimal cost to the search node. And the interesting thing was that we talked about that there was this discussion on admissibility of heuristics. So admissibility here meant that if you had a perfect optimal heuristic, any heuristic which was underestimating or like H, which would be less than or equal to the H star, would be enough for A star to solve the search optimally. Otherwise, it would not be. So on the right, this is a graph where you can see that the perfect heuristic, if one existed, or if it exists for certain search problems, any function below the optimal heuristic would be admissible for A star search. And anything like H5, which is above the optimal heuristic, would not be. So the point here is that A star, being an optimistic search algorithm in that sense, would want a heuristic that underestimates the optimal heuristic. Now note that the difference with the rollout graph on the left is completely opposite. All the heuristics are essentially the blue line, the horizontal blue line is essentially the optimal heuristic, which was calculated by the optimal dynamic programming approach. All the heuristics lie above the optimal heuristic line. And what rollout does is it's using an overestimate to bring back. So if you imagine a heuristic curve with different search nodes, either you can approximate by all the heuristics that lie below that curve and bring it closer to the optimal, which is happening for the A-star search on the right graph. And for the rollout, it's essentially that you can bring down all the heuristics that are performing far away or way worse than the optimal and bring it closer to the optimal heuristic. So that's like these two methods are pretty much connected and also different in certain ways. But this is how at least you can think of the different methods to approximate or get a good heuristic based on what search algorithm you use. Which is why rollout in a sense, or the Wordle game in a sense, is a search problem in a deterministic POMDP setting. That's all. Yeah, thank you. Yeah, any questions about anything? Yeah, please go ahead.
So when you're describing your tree search algorithm, would it have been useful to do pruning ahead of time, or?
So at least that is done for, okay. We did that in a way, first in optimal solution approaches, at least the people who have worked for the optimal solution, they did do some pruning, use some pruning techniques because the total graph is just enormous in that sense. So some of the words which would just defy certain basic constraints, which can easily be pruned at certain stages of the game. In our setting, you can think of when I'm saying that, let me go back to that. When I said that I could just take the top K guess words to perform the rollout. Instead of like taking all 100, I just took top 10. I'm essentially pruning away the less performing 90 guess words.
Okay.
So I do not have to perform a rollout on all of those in that sense.
Right.
So yes, pruning techniques are definitely helpful and way more helpful in optimal solutions at least. Intuitively. Yeah.
But this would be like an AO search because you already know what end node you want.
Yes, you already know what the possible end nodes could be. You have, so in that sense, if you have say 50 possibilities, there's a uniform distribution over those.
Okay.
And I don't know which one it could be, but all of them have an equal uniform probability. And I would just perform a rollout for all those 50 possibilities and see which of my starting words can solve those 50 games in the with the minimum cost.
That makes sense.
So yeah,
Thanks.
Okay, that's all. Thank you so much. And you guys can just leave the attendance sheet and the cheat sheets here.